this last video for this lecture, I want to briefly talk about some other good results that you should be aware of about tensor products. I don't want to give full proofs here. I definitely encourage you to look up the details of the proofs in Conrad's notes or the corresponding statements in Dummett and Foote. But these are results that you may end up wanting to use on a qualifying exam in the future. So you should be aware of how these things work, even if we're not going to do all of the proofs in lecture. All right, so theorem 4.3 in Conrad's notes says, if you take ideals I and j of your commutative ring with identity R, then we know that R mod I and R mod j are also R modules. So R is an R module over itself. It's a module over itself. And so is the quotient R mod I and the quotient R mod j. So the result is that there's a unique R module isomorphism from R mod I tensor R mod j to R mod the ideal given by the sum of I plus j. And where does this isomorphism come from? It's going to send, you have an element x in your ring, you take the image in the natural projection map to R mod I, you get the image of x, tensor, the image of y goes to the image of the product, x times y. All right, so zooming in on a particular case, when you take I equals j equals 0, then this is R tensor R is isomorphic to R. And now there's no reduction going on here, so you just take x tensor y to the product x times y in R. Another special case to zoom in on is if you take R equals z here, then we know what the ideals inside z look like. They're all az or bz for some positive integer. So what we get is exactly theorem 4.1 from earlier, that z mod az tensor z mod bz is isomorphic to z mod dz, where d is the greatest common divisor of a and b, because we know what the sum of az plus bz is. All right, so I don't want to go into the details of the proof, but the big idea is, all right, well, we need an isomorphism. Here we need an R module isomorphism. And an R module isomorphism is an R module homomorphism. It's a linear map from this tensor product to this quotient. So where do linear maps from tensor products come from? You back up and you define a bilinear map out of the direct product of the things in the tensor product. So the key map to think about here is you consider the bilinear map, which goes from R mod I cross R mod j to R mod I plus j, defined by taking b applied to x mod I, or we're using this notation x bar here, b of x mod I comma y mod j goes to xy mod I plus j. So it's this same reduce and multiply map that we saw in the special case where R equals z earlier. So I definitely encourage you to work out the details of this proof. For example, really check that you believe that this map is bilinear. All right, I'll pause and erase, and then we'll talk about another good result to know about tensor products. We'll next discuss theorem 4.5 in Conrad's notes. It says, let I be an ideal of R and M an R module. Then there's a unique R module isomorphism from R mod I tensor M to M mod IM, such that you take your element little r and r, you reduce mod I, and you get R bar tensor M is sent to R times M, and then you reduce mod IM. So one thing to note is that we know that if I is an ideal of R, if we look at I times M, all of the submodule generated by all of the things of the form something in the ideal I times something in M, that really is a submodule. So IM really is a submodule that we can take the quotient by. And yeah, so this is the isomorphism, and it's telling you where elementary tensors get sent. So I want to highlight one special case. You take I equals the trivial ideal, then R mod I is just R, M mod IM is just M. And what we get is R tensor M is isomorphic to M via an isomorphism that takes the elementary tensor R tensor M, just goes to the product R times M. So in particular, now if you take M equals R, then we're seeing that R tensor R is isomorphic to R by this map that takes R tensor R prime to the product R times R prime in the ring. And this is also the same special case that we saw at the beginning of this video for the first result. All right, so if we take the special case where R equals Z, and we let A just be some abelian group, and the ideal I to be NZ, what is this saying? This is saying Z mod NZ tensor A is isomorphic to A mod NA. So what does this NA look like? Is it's all of the things of the form, you take an element in A and you add it to itself n times. Okay, and in this isomorphism, where do elementary tensors get sent? You have an integer, you look at integer m, you look at the corresponding element of Z mod NZ, call that m bar, tensor A, gets sent to take the product m times A, or this group element A added to itself m times, and then you reduce in this quotient A mod NA. All right, so I again encourage you to look at the proof and think about it, but we won't go into those details here. So I'll pause and erase and talk about another result that is good to know about tensor products. This next result has a kind of different flavor to it, but it ends up coming up on exams, so I want to make you aware of it. Theorem 4.29 says that if R is an integral domain with field of fractions K and V is a vector space over K, then if you take K tensor V, this is isomorphic to V via an R module isomorphism, which takes the simple elementary tensor X tensor V to the product scalar, the scalar product of X times V, where this is the scalar multiplication in your vector space. Okay, so the thing I really want to emphasize here is that K is an R module, and V, this vector space over K, it's a K module, but it's also an R module. And you should check that you really believe that that's true. Okay, so this is directly related to the result that we just saw. Theorem 4.5 from earlier implies that if you take K tensor V, this is isomorphic to V if you think of K and V as K modules. And this property of taking X tensor V to the scalar multiple X times V, that's the same property here. But this really is different, because if you think of K and V as K modules, then you can take, in the tensor product, you can take scalars, like you have this action of K on K and this action of K on V, and you can move around these scalars within your tensors. And the scalars here in this example come from K. Whereas in this theorem that we're talking about now, you have many, many, many fewer scalars to work with. They just come from R, this integral domain, not the field of fractions of this integral domain. So the tensor product over K and the tensor product over R really are different objects. One of them is a K module, is a vector space over the field K. And the other one is just an R module. So, you know, there's more things that can go on inside of R modules than in vector spaces over K. All right, so what's the idea here? Well, we need to come up with a R module isomorphism between these two R modules. And where does an R module homomorphism from a tensor product come from? It comes from a bilinear function on the direct product, and scalar multiplication gives a function from K cross V to V. And we know that scalar multiplication satisfies a bunch of nice properties that shows, these properties show that this function is an R bilinear map. So this is an R bilinear map, which gives us an R module homomorphism going this way using the universal mapping property of the tensor product. And you can check that, in fact, this is going to give us the isomorphism that we need here. So let's talk about examples of what this result tells you. If you take your vector space over K to be K itself, K is a one-dimensional vector space over K. K, tensor K, where you think of K as an R module, is isomorphic to K. So in particular, you can prove things like Q tensor Q is isomorphic to Q as Z modules. Okay, so another thing you can do is you can go from your field K to a bigger field containing K. So if K is a field inside of L, we can view L as a vector space over K. And you really should check that you believe that that's true. L is certainly a vector space over L. So what are the things that you need to do to check that it's actually also a vector space over this subfield K? All right, so you should check that. But if you believe it, then R is a vector space over Q. So you can take things like Q tensor R and see that this is isomorphic to R. R is playing the role of V here. K is playing the role of Q. And this is an isomorphism as Z modules. OK, so I'm going to pause and erase, and I'll talk about some final things, properties of tensor products that you may want to use at some point. The last thing I want to do in this lecture is highlight some properties of tensor products that you should be aware of. First, Theorem 5.1. There is a unique R module isomorphism between M tensor N and N tensor M, that the order in which you take the tensor product of your two R modules doesn't matter. Where does this send elementary tensors? M tensor N goes to N tensor M. So this is something you would certainly expect to be true, and you can check that this really is true by coming up with the right bilinear map from M cross N that gives you this R module isomorphism. All right, Theorem 5.2 says that the tensor product satisfies a certain kind of associativity, that there's a unique R module isomorphism from M tensor N, tensor P, to M tensor N tensor P, where we send the elementary tensor M tensor N, tensor P, to M tensor N tensor P. So again, this is something you would expect to be true, and you can check the details that there really is an R module isomorphism that you can write down here. All right, the next result is, again, something that you would expect, that the tensor product behaves nicely with respect to taking the direct sum of two modules, that M tensor N plus P, the direct sum, is isomorphic to the direct sum of M tensor N and M tensor P, where we send the elementary tensor M tensor N comma P, this element in this direct sum, to M tensor N comma M tensor P. All right, the last thing that I want to talk about goes all the way back to when we first started talking about bilinear maps as motivation for the tensor product. We had said that bilinear maps from M cross N to P correspond to linear maps from the tensor product to P. And we know that the set of all R module homomorphisms from one R module to another, in fact, is an R module. And I said that the set of all R bilinear maps from M cross N to some R module P also is an R module. And in fact, these R modules are isomorphic. And the idea is, if you have a bilinear map from M cross N to P, it's associated by the universal mapping property of the tensor product to a unique linear map LB from the tensor product to P. And you can show that this correspondence from B to LB gives an R module isomorphism. So these results are not the kind of thing that you would be asked to prove on an exam, but there may be places where you want to use these kinds of results. Things like the fact that the tensor product of a direct sum is a direct sum of tensor products. So you should be aware that these exist. I definitely encourage you to check out the proofs and make sure that you understand the main ideas. but you will not be expected to prove results like this on an exam for Math 206B.